Hello folks, welcome to the next episode of Electromagnetism. Today we're going to begin with a lecture on Gauss's law. Gauss's law helps us find electric fields in an easy way. Recall that the electric field is defined as K, which in SI units is 1 over 4 pi epsilon naught, Q over R squared, and since it's a vector, we need to know which way it's pointing. You may also write it, which is exact same idea, but you can also write it as Q over R cubed, but with the R vector instead of R hat, which is another very common way to write it. So now, here's the idea. What if you have a very strange charge distribution, such as a sphere, or a cylinder, or an infinite plane? If you have any one of these three symmetrical infinite charge distributions, that's where Gauss's law comes in handy. Gauss's law tells us the following. It tells us that the dot product of the electric field vector, so if you have a positive charge inside, the dot product of the electric field vector with the area normal unit vector, so for a sphere, for instance, the unit normal area vector looks like this. It's normal to all parts of the sphere, right? So for example, if this is the part of the sphere we're talking about, these are the unit normal area vectors. For a cylinder, it might look like this. For this part of the cylinder. For a flat plane, infinite flat plane, you have two area normal vectors, one upwards, one downwards. So that's the idea. Those are all of your DAs, your tiny little unit normal area vectors. If you take the dot product of that with your electric field, Gauss's law tells you that's equal to the amount of charge that's enclosed over epsilon naught. And in fact, this is a direct reflection of Maxwell's equation, which says the divergence of the electric field is rho over epsilon naught. Rho, Q. Why the difference? Well, divergence, these kind of gradient nabla operators are kind of taking a zoomed in view of the entire charge distribution. So it makes sense that it'll have a zoomed in version of the charge, which is the charge density. Whereas if you integrate over the entire space, then you're going to get the charge enclosed over epsilon naught. So now let's go ahead and take a look at some example problems. Here is another view of problem 1. Alright folks, let's take a look at problem 1, which says a spherical volume of radius A has the following charge density. The volume charge density is kr to the fourth. We are asked to find the electric field outside the sphere and inside the sphere. And then we are asked to find the electric potential given that the ground is at a spatial infinity. Okay, so let's start with part 1. How can we figure out the electric field? Well, we have to employ Gauss's law. Gauss's law tells us that if we construct a Gaussian surface inside, then the following holds. The dot product of the electric field with the unit area vector is equal to the charge enclosed over epsilon naught. Now, let's take a look at inside. Where is all of the charge? Well, the charge is throughout the sphere. It's not a spherical shell, it's a spherical volume, right? And so we cannot say that the electric field inside is simply 0. We have to calculate it. So EDA for our sphere, since the electric field and the radial area unit vectors are in the same direction, we're simply going to have E times A is equal to the charge enclosed over epsilon naught. But what is A? For a sphere, A, the surface area, is 4 pi r squared. So we're going to have E times 4 pi r squared, where r is simply the radius of our Gaussian surface. And this is equal to the charge enclosed over epsilon naught. But what is this charge enclosed? Well, we have to figure it out. So let me grab my red marker and use that to figure out the charge enclosed. The charge enclosed, since this is a volume charge density, is going to be rho times V. Well, what is rho? Rho is kr to the fourth. So let me bring this over here. Q, hopefully you can see all the way up to, well, to the end. So we're going to have rho times kr to the fourth. So kr to the fourth times v. Well, for a sphere, v is 4 pi r squared dr. Let's make all of these r prime since we're going to integrate these from 0. Actually, I screwed up. Since, and this is very important to note my mistake on camera because it is plausible that you'll make it as well. So far, I have not made any actual mistakes, but it's much easier to find the electric field outside and then find the electric potential from there than to find the electric field inside and find the electric potential from there. Why is that? Well, it's because the ground for the potential is at spatial infinity. So it's better if we start by finding the electric field outside. Nevertheless, we can carry on using this method and we'll get the exact same answer. Let me show you. So, where is our radius starting from? It's starting from 0 to wherever we want to stop. And so this is going to be 4 pi k times the integral of r prime to the 6th dr prime from 0 to r. And what is this going to become? This is going to become 4 pi k r prime to the 7th over 7. Now I can plug in my bounds. This is going to be 4 pi k r to the 7th over 7. Well, okay, that wasn't too bad. And so that is the charge enclosed. Now I'm going to put that down right here. So the electric field times 4 pi r squared is equal to Q. Now I know what Q is. Q is 4 pi k r to the 7th over 7. 4 pi cancels out. Don't forget your epsilon naught, folks. R squared goes into r to the 7th 5 times. And so we're left with the electric field. Hopefully you can see if I write down here, the electric field inside of this spherical volume is equal to k r to the 5th over 7 epsilon naught, and it is radially pointing outwards since we have a positive charge density. So this is the electric field outside of our charge distribution, and inside of our charge distribution. R is less than capital R. What about inside? What about outside? Well, outside we're going to be encompassing all the possible charge, right? So that's going to stop. Not the upper limit will no longer be R. It'll be A, the radius of our spherical volume. And so the electric field outside, hopefully I can write here and you'll see, is going to be the exact same thing. R is greater than capital R. But now we're going to stop all the way outside, which is R is equal to A. So over here we had kr to the 5th. Now we're going to have ka to the 5th. Ka to the 5th over 7 epsilon naught in the r hat direction. This is the electric field outside. As you can see, it is a constant. All right, now let's take a look at part B, which is to find the electric potential inside and outside our sphere. All right, so the electric potential, remember, is given as give us the electric fields. Well, we know what the electric field is. Well, how do we find the electric potential from the electric field? Well, all we have to do is integrate. Remember that the potential is simply minus the integral of the electric field with respect to some path, dl. So let's integrate these two and get our electric potentials. So let me first write out my electric field in this format, since I think it's more helpful. Inside my sphere, I'm going to have kr to the 5th, 7 epsilon naught as my electric field. And outside my sphere, my electric field is going to be constant, ka to the 5th over 7 epsilon naught r hat. And so now that I have these, finding my electric potential is nothing but a matter of integration. So first let's begin with, as I said before, you should always start with the region, the electric field region that's closest to where your ground is. And since our ground is at spatial infinity, let's start outside everything. So integrating this with respect to r, we're going to have the potential is minus ka to the 5th over 7 epsilon naught dr as we go from r is, let's say r prime, as r prime goes from infinity to some point outside. And so this is going to be minus ka to the 5th over 7 epsilon naught. I just noticed that I made a mistake. Remember that when we had the Gauss's law, we had 4 pi r squared is equal to q enclosed over epsilon naught. Don't take shortcuts, folks, because that's how we arrived at r to the 5th, because we had r squared cancel out with r to the 7th. But here, I just replaced r with a, and then I forgot to put down, I forgot to take down that factor of r squared that stays on the bottom. That stays on the bottom. And so that's why my integral was looking all funny. There should be an r prime squared here. And so when I integrate this, I'm going to get minus ka to the 5th over 7 epsilon naught, 1 over r prime net times negative, which makes this a positive, as r prime goes from infinity to r. And so that means our potential outside is simply going to be ka to the 5th over 7 epsilon naught r. This is our potential outside. Okay, I have fixed my electric field outside as well. I forgot to put down this factor of r squared. Now let's do our electric potential inside. Electric potential inside is going to start by setting the outside one to the radius of our spherical volume, because imagine you're piercing in. You have to always start from the ground and then stop as soon as you hit the radius and set this one, the outer potential, to the radius. So it's going to be ka to the 5 over 7 epsilon naught instead of r, stopping at the radius, which is a. Okay, minus the integral of this stuff. So kr to the 5th over 7 epsilon naught dr. Let's make these primed, and we're starting from the outer radius and stopping somewhere inside, right? So this looks kind of messy. Let me bring it down here. I'm going to have ka to the 5th over 7 epsilon naught a. Okay, don't confuse this r. This is an upper limit on this integral. Minus this integral. Now what is this integral? That's going to be r prime to the 6th over 6. So I'm going to end up with minus k r prime to the 6th over 6 times 7, 42 epsilon naught, as r prime heads from a to r. And so this is going to be ka to the 5 over 7 epsilon naught times a minus k over 42 epsilon naught r to the 6th minus a to the 6th. That, ladies and gentlemen, is the electric potential inside. But there's one mistake left to be found. Can you see it, folks? It's this exponent right here. It should not be a 5, because we never canceled out a factor of r squared from that numerator, right? So this should stay a 7. Remember, this r is to the 5th power because we canceled out r squared away from it, leaving us with r to the 5th. But this a is untouched, leaving it an a to the 7th. And this also should be hence an a to the 7th. And thus this also should be an a to the 7th. So please be very, very careful. This too should be a to the 7th. Please be very careful with your math. As you can see, just skipping Gauss's law for this part, just thinking that I had it in the bank, caused 1, 2, 3, 4 errors. So please be very careful with your math, and let's check out the next problem. Here is the problem. All right, folks, let us begin problem 2. All right, folks, let's take a look at our problem. An infinitely long cylinder is hollow down its central region r less than a, but carries a volume charge density gamma r for r between a and b. Find the electric field within the hollow region, within the annular region, and outside of the entire charge distribution, and find the electric potential in each region if the potential vanishes on the axis. So on this axis right here. Down this axis is the ground for our electric potential, aka where our electric potential equals 0. In other words, you might hear surfaces being electrically grounded, that means simply that their electric potential is 0. Okay, so let's figure this out. First things first, find the electric field in all regions. Let's start with that. So I'm going to first figure out what are all the regions. Well, first you can be inside the hollow part, which is r less than a. You can be within the annular part right here, like for example here or here. That means r is between a and b. And finally, you can be outside of the entire charge distribution, in which case r is greater than b. So let's figure out first r is less than a. That's perhaps the easiest because inside there is no charge, right? It's hollow. It's hollow down its central region r less than a, right? So there is no electric field within that hollow region because there's no charge to begin with. What about in that annular region between r is a and b, where all of my volume charge density is? Well, for that region, I'm going to need a Gaussian surface, right? So let me construct a Gaussian surface. So maybe something like this. And since this is a cylinder, it's an infinitely long cylinder, I'm allowed to use Gauss's law. This Gaussian surface is maybe of length L, right? And so let's write down Gauss's law. We have the integral of E dot dA is Q enclosed over epsilon naught. Okay, so in this case, A is what? It's the surface area of the cylinder, which is going to be 2 pi r times L. And that should be equal to the amount of charge enclosed. Well, I'm going to need to figure that out on its own. So because we have a charge density that varies with the radius. So let's see. The charge density starts from r is a and stops to wherever I'm stopping. Let's say r prime equals r. So I'm going to have something like this. The total charge for a volume charge density is rho times v, the density times the amount of volume you're enclosing. So in this case, it's going to be rho, which is gamma r. And what's the volume for a cylinder? Well, r d theta. Let me put primes here. R prime d theta, that's a length. Let's push it out so that it's an area. So that's going to be a unit of area. And now it is a length, a volume. So these two make it an area. All three of these make it a volume, right? Now, yeah, let's go ahead. Let's do it. So let me put down the triple integral. Since this is a volume charge density, I need to figure out the whole volume. Theta, in fact, it's much better to use phi, which is the actual axial angle for the xy axis in physics. Phi is going to go from 0 to 2 pi. R is going to go from A, which is where my charges begin from, right? Because that's the end of the hollow region, to R, wherever I'm stopping. And Z is whatever the length of the cylinder is. That's pretty simple. So let's integrate away phi and Z. Those are pretty easy. That's 2 pi L gamma times the integral of r prime squared dr prime as r prime goes from A to R. Okay, so this is going to give us 2 pi L gamma r prime cubed over 3. And of course, the limits of integration dictate that r prime go from A to R. So this is going to become 2 pi L gamma r cubed minus a cubed over 3. That is the total amount of charge enclosed for a Gaussian cylinder of arbitrary radius within this annular region. And so the electric field is going to equal what? Let me erase this stuff now that we don't need it anymore. This is going to equal 2 pi L gamma r cubed minus a cubed over 3 epsilon naught. Don't forget your epsilon naught. That's just q. You got to divide q by epsilon naught. Right? Now we're going to do some cancellation. 2 pi L and 2 pi L cancel from both sides. And we're going to have an R go to the other side for the electric field. So that means our total electric field for the annular region is as follows. It's going to be all of this, which is gamma r cubed minus a cubed over 3 r epsilon naught r hat. Okay, now let's find the electric field outside the entire charge distribution. Now I could just, pretend like I've got it in the sack as before, but I don't want to risk making any mistakes. So I'm going to go through the entire process of Gauss's law one more time and figure out the electric fields manually outside. So Gauss's law, once again, says the following dot product is equal to Q enclosed over epsilon naught. Now in this case, we're looking outside the charge distribution, outside everything. So our Gaussian surface is going to be a cylinder that encloses everything and goes outward like that. So we're going to have E times 2 pi r L, again, same idea, that's still the surface area. But now what's going to be my Q enclosed? Well, my Q enclosed is going to be, again, that triple integral. But, is it really a triple integral? Well, not if you get rid of the 2 pi and the L. So let's get rid of those quick. 2 pi L. Okay, that comes from the phi and the z components. So the phi and z variables. But you'll still be left over with the r prime dr prime. And you'll, of course, have your gamma r prime. So you'll have r prime squared again, right? Gamma r prime squared. As r prime goes from A to B. So it encompasses all of the available charge. So you'll have 2 pi L gamma r prime cubed over 3 as r prime goes from A to B. And so now if I plug in my limits of integration, that'll give me 2 pi L gamma A cubed, B cubed minus A cubed over 3 epsilon naught. So let me put that down over here. I'm going to have for the right hand side of Gauss's law, all of this behemoth, 2 pi L gamma B cubed minus A cubed over 3 epsilon naught. Once again, we're going to have some canceling fiasco. So 2 pi cancels out from both sides, L cancels out, and so we're left with almost the same thing. Gamma B cubed, gamma B cubed minus A cubed, since we're now encompassing all the available charge, over 3 r epsilon naught r hat. So there you go. Those are the electric fields in all the regions for this charge distribution, for this infinite cylindrical charge distribution. Okay, now let's take a look at part 2, which asks us to find the potential in each region if the potential vanishes on the axis. Well, the potential vanishes on the axis, which is this one, r less than A. So it's easiest to start there. So remember the potential, let's pick orange. The potential is simply minus the integral of the electric fields over a certain path, dl. So if we integrate 0, that means, of course, we'll get 0. Electric potential inside the hollow region is simply going to be 0. What about here? Well, that is simply going to be the integral of all of this. Let's do it. So the electric potential is going to be minus the integral. So let's pull out all the constants. So I'm going to have gamma over 3 epsilon naught times the integral of r cubed minus A cubed over r. So that becomes r squared minus A cubed r to the minus 1. Right? So r to the minus 1, I might as well just write it as A cubed over r dr. Okay? And where am I going from? Well, think about it. I'm expanding from A to some arbitrary radius. So A to some arbitrary radius. So let's make these primed. So this is going to equal minus gamma over 3 epsilon naught. Now this is a pretty strange integral, but r prime cubed over 3 for electric potential. R prime cubed over 3 minus A cubed ln of r prime. Alright, so now let's finish off this electric potential. We have to simply plug in these limits of integration. We have the upper limit being r and the lower limit being a, which gives us r cubed over 3 minus A cubed ln of r minus A cubed over 3 plus, since minus minus makes plus, A cubed ln of A. Okay, now let's see if I can make that simpler. First of all, if we bring these elements together, I'm going to have, hopefully you can still read, minus gamma over 3 epsilon naught times, if I bring these two terms together, I'll have r cubed minus a cubed over 3. That's that term. And then when I subtract two ln terms, I can write this as ln of a over r. So minus a cubed ln of a over r. Okay, so there you go. That is everything. And then I can use this negative sign to flip these two. So let me just write, this was the potential. Was it for outside or for this one? Well, since we're proceeding from inside to outside, it's reasonable that this was our potential. So this is going to be gamma over 3 epsilon naught times a cubed ln of a over r minus r cubed minus a cubed over 3. Okay, now I can erase all of this and proceed to find the final potential. Okay, so the final potential is going to be what? Well, first I'm going to integrate this, sure. So let's integrate this. I'm going to have the potential is minus, take out all the constants, gamma b cubed minus a cubed over 3 epsilon naught, and we're simply going to integrate 1 over r dr as we go from, well, where are we going? We're starting now from the surface and then we're expanding outwards, right? So if we're starting from the surface, which has a radius b, and we're going into an arbitrary ending point, this will be our limits of integration, b to r. And so I'm going to have minus gamma b cubed minus a cubed over 3 epsilon naught ln of r over b. But of course, I have to also set this guy to r equals the outer radius b. So when I do that, I'm going to have gamma over 3 epsilon naught a cubed ln of a over b minus b cubed minus a cubed over 3 plus or minus this stuff. Okay, so let me just add plus this term. Folks, a small sign mistake has been made. Because of a small sign mistake, this should be r over a instead of a over r. And thus we should have ln of b over a instead of a over b. Okay, so two small mistakes. Hopefully you caught that. But nevertheless, let's move on. And that's it. Those are the electric fields and potentials for this problem. Thanks for watching. Let's check out problem 3. Here is the problem. Let's now begin problem 3. So here's our problem. An infinite slab with the following volume charge density rho equals gamma x to the fourth exists for x between negative a and positive a. Find the electric field everywhere and the electric potential everywhere if the ground for the potential is right here. So this is the ground for the potential. I'm going to use a different color to denote that x equals 0 is the ground, which means that the electric potential there is 0. And now let's begin. So first part's first, and that's finding the electric field everywhere. That is actually quite standard. We can find that out using Gauss's law, which says that the dot product of the electric field with the normal unit area vector is the charge enclosed over epsilon naught. Now, for this kind of a situation, for this kind of a charge distribution, where you have a charge density rho of x equals gamma x to the fourth between the two infinite slabs. Actually, this whole thing is one infinite slab situated in 3D space, so something like this. It's kind of like a rectangular prism. Something like this. That's your slab between minus a and a. Obviously, it's not to scale or anything, but that's the idea. You have an infinite slab like this, and so we have to find the electric field everywhere, and we're going to do so using Gauss's law. So let's start. So first thing I'm going to do, let me put my pen there, is draw a Gaussian surface, something like this, as before. And here you can see that my flux, electric flux, is going to pierce out of those two sides, giving me twice the electric flux that I would have if there was a flux on only one side. Of course, there's no flux to the upper bottom sides because, well, there the electric field is parallel to the side. And that's equal to the charge enclosed over epsilon naught. Now, what is the charge enclosed? Well, let's figure it out. It's going to be the integral. Now, this is a volume integral, right? So let's first put down gamma x to the fourth. Okay, gamma x to the fourth. By the way, all that this means is that the charge density only exists but when x is between negative a and a. That's all that this means. Nothing to freak out over. So I need some kind of an area volume. So this is a little slice dx, right? If I multiply that little slice dx with the area of my face, that's going to give me a volume, a dv element, right? So this is the total amount of charge enclosed. So this is going to be what? As I go from negative x to x, let's make this x prime here. So I'm going to get gamma x prime to the fifth over 5. Don't forget your factor of a. Okay? And of course I'm going to plug in as x prime goes from negative x to x, right? So this is going to give me, well, 2a gamma x to the fifth over 5. Okay, well now I can plug and chug, so let's do that. So I'm going to get 2ea is equal to 2a gamma x to the 5 over 5 epsilon naught. 2a cancels out from both sides, leaving me with an electric field for staying within. So when x is within a, the electric field is what? Gamma x to the fifth over 5 epsilon naught. And of course, what's direction? Well, it's just I hat. And I don't have to create two electric fields. I don't have to break up the electric field into the positive and negative region for x, because this odd power communicates the direction inherently, right? If I'm in the positive side, if x is here, then x to the fifth is positive, hence the electric field is that way. If x is negative, x to the fifth is also negative, and so the electric field is that way. And that odd power ensures that I have that quality. So here's my electric field inside the slab. Now what about outside the slab? Well, that's where it gets a tad bit complicated. If we're outside the slab, the charge enclosed is going to start from negative a and stop at a, positive a. So I'm going to go from negative a to positive a, giving me 2a gamma lowercase a to the 5, right? So that's going to give me the same exact thing, but now the electric field is going to be constant. So the electric field, let me put a vector symbol here. The electric field outside is going to be x, let's first do greater than a. So let's say the electric field here, over to the right side. The electric field on the right side is going to be 2a, whoa, going a bit too fast. Let me not forget to cancel stuff out. Remember, I'm going to have 2ea by Gauss's law. 2ea is equal to the charge enclosed, 2a gamma a to the fifth over 5 epsilon naught. 2a cancels out from both sides, and so I'm left with the electric field outside when x is greater than a is equal to gamma a to the fifth over 5 epsilon naught. So the exact same, except x becomes a because we're enclosing all of the charge, and now we got to break up the electric field into x greater than a and x less than a, because now since the electric field's magnitude is a constant, it can no longer do the work of telling us the direction inherently. So we got to manually put in that minus sign. Minus gamma a to the fifth 5 epsilon naught I had. So here's the electric field in all three regions. Okay, so now let's find the electric potential in all regions if it vanishes on the axis. So first let me organize this information. So now I'm ready to find my electric potential. The electric potential, remember, is defined as follows. If I know my electric field, then the electric potential is simply minus the integral of the electric field over some path, dl. So let's start off with where the ground is. The ground is defined to be on the axis, so that's where we should start. This is the region closest to the axis, so we can just integrate it and put a negative sign on top. So minus the integral of gamma x to the fifth over 5 epsilon naught. Now what's my dl? Well, I'm heading out this way, so it's going to be dx, right? So let's do it. Now wait a minute, where am I starting from? I'm starting from here, which is x is 0, and I'm going to some arbitrary point, let's say x. So let's prime these variables. So now let me integrate. I'm going to have minus gamma x prime to the 6th over 30, since 6 times 5 is 30, epsilon naught as x prime goes from 0 to x, which gives me minus x to the 6th over 30 epsilon naught. Okay, great. I've got my potential. What else can I say? So let me straight up write my electric potential here. So my electric potential, V, is equal to minus gamma x to the 6th over 30 epsilon naught. Okay, well, let's carry on. What about the potential on the right side? Well, on the right side, first and foremost, I've got to set this guy to where it stops, which is A. So this is going to be V is equal to minus gamma A to the 6th over 30 epsilon naught. And now I can integrate this. But this is, of course, a constant. So minus the integral of this is simply going to be what? Well, I'm going to integrate starting from A to some arbitrary stopping point, gamma A to the 5th over 5 epsilon naught dx prime. So this is going to give me the electric potential is minus gamma A to the 6th over 30 epsilon naught minus gamma A to the 5th. Okay, now gamma A to the 5th over 5 epsilon naught x prime is going to become x minus A. Okay, so that is my electric potential for the second region on the right, going to the right side of the charge distribution. My electric potential is gamma A to the 6th 30 epsilon naught minus gamma A to the 5th over 5 epsilon naught x minus A. And now let's take a look at the final charge distribution, the final field, which is this. So for this one, I'm going to have much the same thing, this guy, but now it's coming over, now it's stopping at minus A. So I'm going to have minus gamma, minus A to the 6th is still, well, A to the 6th, right? So over 30 epsilon naught. Now this guy is going to go from minus the integral from, where am I starting? Well, I'm starting from a negative x, and I'm going I'm starting from a negative A, and I'm going to a negative x, right? Okay, and so integrate this stuff. Hang on, this is a negative. Right, so I've got to be very careful with my signs here. Negative gamma A to the 5th over 5 epsilon naught dx prime. Alright, so I'm going to have negative gamma A to the 6th over 30 epsilon naught, no problem. Okay, and now for this stuff, I'm going to have plus gamma A to the 5th over 5 epsilon naught times. Now here I've got to be careful. This is a minus x minus A, so it's going to become minus x plus A. Now let's think about this. If x is minus A, this is going to become minus A, which doesn't work. So I've got to keep this a plus, so then when x is minus A, this term drops out and I'm left with this. And for this guy, when x is minus A, when this guy x is minus A, they have to match. And so they only match if I have x plus A inside here. X plus A. Okay, so there you go. That right there is the potential on the left side. Here's the potential on the right side. And here's the potential inside the slab. Thank you for watching. We'll see you next time.